there's the camera. Hello, everybody. Welcome to this Astro Coffee Hangout for this week. My name is Tony Darnell. I work at deepastronomy.space, and today we are going to have a hangout where we discuss the exoplanets and the science that are hoping to be done and found by the new TESS spacecraft that that most of us saw launched a couple of weeks ago, the Transiting Exoplanet Survey Satellite, and it is going to be the follow-up space telescope to the venerable Kepler Space Telescope, which has helped reshape our views of the universe like never before. It has discovered, I think it was designed to find planets about the size of the Earth as they transit between us and the star, and boy did it do that. Well, they've built another telescope, folks, another spacecraft, and they've launched it, and it's up there, and we're getting ready to start taking data. But today we're going to talk with some scientists who have written a paper outlining what we might expect to find with this wonderful telescope. So let me bring up my my cohorts here, and with me today is my co-host, Dr. Carol Christian from the Center for Emerging Media. Hi, Carol.
Hey.
Hey, good to see. Oh, wow, you got a TESS shirt. I'm jealous. That's nice.
Yes, I do.
Oh, that is really cool.
I do.
So that's what you get for when you work at NASA, folks. You get all the cool swag. No.
You have to know the Land's End code.
Oh, there's a code. So it's on Land's End, and there's a code for it. Well, now you got to share it with us. Can anybody buy it?
And I chatted up the lady who knows all the NASA logos.
So it's one of those need to know kind of things.
Because I knew there was a test.
Cool.
A test shirt.
All right.
So,
well, don't you worry, folks. Well, don't you worry, folks. I'm going to design a TESS shirt for Deep Astronomy space fans that'll be available soon. So don't you worry. Not only that, there'll be a JWST one and a whole lot of other stuff. So good. All right. Well, let's see. So today, my guests are in the upper. Let me start with the upper left. Is Dr. Joshua Pepper. He is from Lehigh University and one of the co-authors on the paper we're talking about. And right next to him is, is Dr. Thomas Barclay from the Goddard Space Flight Center at NASA. Welcome, guys, and thanks for taking time out to talk about your paper that you wrote.
Yeah, absolutely.
Hey, we're excited to be here.
Okay, so
thanks for having us.
Yes, and the big question, I was going to set the stage by showing you all of the exoplanets that we know about so far, but we'll just briefly set the stage. The Kepler Space Telescope has been in orbit since 2009. It's been up there as K2, where it's orbiting the Earth, orbiting the Sun with the Earth, and finding and still doing science. But it is rapidly losing fuel. It's just running out of fuel because of normal wear and tear. And so it's giving way to this new telescope called TESS. And why don't we start by just, a lot of us know what TESS is, but maybe Thomas, you could give us a little overview of the TESS spacecraft, and I will show this lovely animation that you gave us while you talk.
Okay, so Kepler was a statistical mission. It was there to tell us, are planets common or are they rare? And unequivocally, Kepler told us planets are common, planets are out there. However, most of Kepler's planets are relatively far away. They're not the best planets to study in great detail. So this is where TESS comes in. TESS is built, flown, we're going to operate it to find the best planets to study with future telescopes from both the ground and from space. So TESS is a relatively small spacecraft. It's about the size of somewhere between a washing machine and a fridge. It has 4 cameras, and each of those cameras are used to observe a pretty large patch of the sky. Each camera observes a patch of the sky much larger than say, the constellation Orion. And we have 4 of them observing all at once. Each of those cameras is pretty large. You can see how we'll observe there. The 4 cameras observe, and then we'll observe one patch of the sky for about a month, and then we'll rotate the cameras around. We'll observe a new patch of sky, and then over about 13 months, we'll observe a whole hemisphere. That's about a year.
Yeah, and let's see.
After that, we'll carry on.
No, go ahead. Go ahead and finish.
Oh, I was going to say, after a year, we'll turn the spacecraft upside down, and we'll do the next hemisphere. So in 2 years, we do most of the sky.
Is that
the first year we do the south, the second year we do the north.
Is that what this animation shows here? Let me just Let me go back to this.
Yeah, that animation is showing you how we observe. You see those 4 cameras, and then we do all our 13 sectors, and then we go upside down.
Yep, and then do the whole sky. And then when you're done, there it goes. And how many times will TESS be doing this?
It'll do the southern ecliptic hemisphere once and the northern ecliptic hemisphere once, and that's our 2-year primary mission.
Okay.
And after that, our primary survey is done.
And if I'm not mistaken, there's 2 modes of operation with the cameras. One of them is a wider field of view than the other. Is that right? One of them is
Yeah, so the way that it works is that each of those boxes, each of those squares that you see there is the observation of a huge patch of the sky by a whole camera. But we don't have enough bandwidth to download every single pixel from every single camera observation of that patch of the sky. So what we're doing is we're selecting a small fraction of all the stars that TESS can see, and we're going to download just the pixels around those stars to measure their brightness over time to find transiting planets around them. And then we download the entire camera field of view on a longer time scale that we're able to download.
Oh, I see. So the data itself isn't really different. It's just that you're downloading specific portions of it. When, like, if something is particularly interesting, you'll just download that around the pixels around that star, and then everything else will still make it down, just not right away. So it's a faster way of a quick look, I guess, is the way to look at it, right?
It's basically a faster way and a more detailed way of looking at just those pre-selected stars.
Okay, all right. Well, here, when it's all said and done, is the way in the coverage, the sky coverage of TESS as it goes through. What is that red circle at the top?
So that red circle near the top is the TESS continuous viewing zone.
It always sees this.
In that previous animation, for an entire year, every time one of those sectors observes, the cameras are overlapping. So in that sort of the bottom there, that's what that red circle represents.
Okay, all right, I see. Good.
So
And
there'll be lots of data there.
right.
Oh, yeah.
And let me show this animation because it's very important to understand why you're looking at this for such a long period of time. This is how TESS finds the planets. Do you want to describe this? Why is it stuck?
Yeah, I can talk about this. So the way TESS and Kepler and most of the planets we've found, we find them is using the transit technique. So the way the transit technique works is you look at stars, you wait to see some stars that a planet will pass in front of during its orbit as it's going around those stars. If they're aligned just right, the planet will pass in front, block some starlight, and tell us it's there. The bigger a planet is, the deeper the transit, the more likely it blocks. So by measuring how deep the dip is, we know how big the planet is.
Yeah, this is supposed to be animating.
These transits don't happen randomly. They happen once every time the planet goes around its star. So by measuring how frequent these events happen, we can tell how far away the planet is from its star, and therefore what kind of temperature the planet might be.
So that's it, and this is supposed to be, for reasons I don't understand why it's not. There it goes. Now it's finally kicked in. Okay, so here it's actually animating. So you can see that as the planet moves between us and the star, there's a dip in brightness. This is highly exaggerated because you wouldn't see this much really, but you can see a bigger planet like Jupiter making a bigger dip in front of the star than an Earth-sized planet was, and those Earth-sized ones we're very interested in. But you need more than one observation of this star to get this light curve, don't you? So you need to keep going back and taking more and more and more of these pictures. And when I look at the coverage of the TESS, the way it's imaging, it needs to go back to that same area of the sky periodically, doesn't it? It can't just take one shot and then never go back again, right?
Right. So what's going on is that during each of those sectors that you saw observing, each of those sort of long string of 27-day observations. So for each of those, if you go back to that previous one, each of those rectangles is a continuous set of 27.5 days where TESS is staring at all the stars in that field continuously.
And taking many, 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 many pictures, right? Not just staring at one spot. What is he?
Right. What it's doing is
I'm
Yeah,
sorry.
it's basically taking a picture of every single star in the field every 30 minutes.
Every 30 minutes, okay.
And then for that set of every pre-selected star that we were talking about, it takes a picture of them every 2 minutes.
Okay, cool. All right, so that is an intro into TESS, folks, and I wanted I want to take a quick moment to remind you that you are watching the Astro Coffee Hangout. We've been at this for 15 minutes, and I wanted to mention that we are live right now, and you can ask questions of our guests in two ways. You can do the YouTube chat, which I'm looking at now, and it's quite active right now. So hey, everybody, it's good to see you. And I'm also looking at the Discord server for Deep Astronomy, where people are there. Peter Q's there anyway, and so those are two ways you can ask our guests questions if you want to. So please do so as we go on, and I'll take a read of what's going on. So let me pull everybody up, and okay, so let's get to your paper. TESS is just launched. It is on its way in its orbit. Oh, we should probably show its orbit, shouldn't we? Don't I have a thing that shows its orbit? Is it that? No. Here it is. Let me get rid of this. Let's talk. We should show its orbit real quick. So this is the orbit that TESS will be in. Let me zoom that up a bit. And it is in a. Well, why don't one of you explain this to us? Joshua, maybe.
Actually, I think Tom's the one who knows the most.
Okay,
about
then Tom, help us.
Okay. Sure. So TESS launched on April 18th. It launched into an orbit that takes it about out to the distance, approximately the distance of the moon, and then all the way back in again, close to the Earth, about the height that Hubble orbits the Earth. It does several of these orbits, about 3 of them, steadily increasing the eccentricity or making the orbit more elliptical and less circular for the next month up until about May 18th. And then on May 18th, it has what we call the lunar encounter. That's when it flies pretty close to the moon. The moon gives it a real big kick, knocks it into a different orbit, an inclined orbit. And then that orbit is our final orbit, the orbit we're going to fly in. So the reason we're in this orbit is that it gives us kind of the best of both worlds. We spend most of our time quite far from the Earth. So it's a fairly steady state. It's the same temperature. It's a very quiet environment. But then once every 13 and a half days, which is our orbital period, we come in, swing pretty close to Earth. And that's when we downlink all our data. So we get a stable environment, but we are also close to Earth for some of the orbits, so we can have high bandwidth.
And
so the green orbits that are different sizes are the ones you're speaking about that it's doing now until it encounters the moon?
That's right. So first we're doing these green orbits, and it's getting steadily more and more elliptical.
And then the red-yellow thing is when it gets kicked out, and the cyan orbit is the one that you'll be in?
That's right. That's our science orbit. The
great.
Rather affectionately named PLEP, which is post-lunar encounter perigee.
Okay.
And then Plea must be apogee, right? So
That's right. That's right.
Yeah.
Okay.
Yes, very nice.
Plea and plep. Okay, good.
If you were a ballet dancer, you would say plie.
Plie.
I mean, TESS is really doing almost a ballet with the moon.
There you go.
It's
Nice.
hard. It's hard to get in these weird polar-like orbits, isn't it? I mean, they had to do something similar with the Parker Solar Probe, getting it into the sun. They had to do all these flybys to get it there, because going into the inner solar system is hard. So, I guess it's not easy to get it kicked out into this orbit, is it?
I mean, some of the most fun I've had is chatting with our flight dynamics team at Goddard Space Flight Center here, and all they do is the maths of how you get spacecraft in and out of various orbits and wherever you want in the solar system at the right speeds. It's it's close enough to magic, this kind of mathematics.
And it is cool to watch for sure. All right, well, so now let's get to your paper, where you have written, and by the way, folks, the link to that paper, as always, and all the Astro Coffee Hangouts is in the description box below. I was perusing Astro PH the other day, and I came across it, and these guys were kind enough to join us and talk about it. All right, so We know what Kepler has done for us. We know what the ground-based telescopes have done for us. It measure these tiny dips in brightness, and we've got other ways of finding exoplanets. But you guys have wrote the idea of the paper is, what can we see with TESS? So why don't can you tell us a little bit about how you know what you're gonna? Well, I guess I should read the title: A Revised Exoplanet Yield from the Transiting Exoplanet Survey Satellite. So you guys are already talking about what you expect to see, right? Right?
Yeah.
Okay.
So what we're doing is we're really building off of work that's already been done by some really fantastic astronomers, Peter Sullivan and Luke Bauma, who have already done some really thorough estimates of what TESS would detect in terms of what kinds of planets, how many of them, what sizes they'll have, what orbits they'll have. And what we've done here is that the previous papers didn't actually know exactly which stars would be the primary ones that TESS would observe. And what we've done is we've taken the actual target list that TESS is going to observe, those pre-selected high-value targets, high-value stars that are scattered throughout the full footprint of all the area in the sky that TESS is looking at. And then we've said, based on the sizes of those stars, their brightnesses, and other properties, then how much more precisely can we say how planets of what kinds TESS will detect?
And so, and you say, and that's so this is the part I was getting at earlier, but I didn't quite ask it right. And that was in your paper, in your abstract, it says, in the TESS 2-minute cadence mode, we estimate that TESS will find 1,250 plus or minus 70 exoplanets with 90% confidence, 250 smaller than 2 Earth radii planets. So this 2-minute cadence, this is the part where we pick out that small bit, the pixels around. Is that that part?
That's right.
Okay. So
that's right.
And those are the high value targets you just talked about, right?
That's right.
Okay. All right. Good. Now that I understand more fully what you're talking about, so you're grabbing these high value, high interesting targets, which were interesting already because of Kepler?
Because of enormous work of hundreds of scientists taking all these surveys of the sky. So there's various surveys called things like TUMAS and Tycho and UCAC and Gaia. And they've measured the properties of stars. And what we did was we took all of those lists of literally hundreds of millions of stars, and then we narrowed that down to the stars that would be the most valuable for which we could find planets orbiting them. So basically what that means is very bright stars relatively nearby the Earth that are also relatively small, because a smaller star makes it easier to find a smaller planet.
Okay. So you're basing this on work done by all the other surveys that are out there, and these are planets that are currently not low. We have them. They have not been seen. They have not been measured. I guess what's getting me about this is that this is very specific. I mean, furthermore, we predict an additional 3,200 planets will be found in full-frame image data orbiting bright dwarf stars, and more than 10,000 around fainter stars. Okay, and then you predict that TESS will find 500 planets around M dwarfs. This is very specific stuff. So I'm trying to get how these numbers are being. I mean, I know that you're basing it on work that's being done. Are these models that other surveys have put together? Because they're not found. We haven't found them yet.
So part of the beauty of Kepler is it taught us how common planets are. That was the goal of Kepler, and it succeeded spectacularly well.
That's right.
And TESS can really only exist because Kepler has told us planets are common. So now we can go and build TESS to go and find the planets, and we know the planets are out there. Kepler has given us what we call occurrence rates of planets. We know how common Earth-sized planets are. We know how common Neptunes are and Jupiters are. So really, while we are simulating this and we're making estimates based on a bunch of things, we have a reasonably good handle on how common planets are, and we have a reasonably good handle on the stars that are out there. Cool. So we mix the frequency of planets, we mix the stars that we're going to observe, we jumble them up, and we say, what do we think we're going to find? And that's what we did here.
So from Kepler alone and similar studies on the ground, we know, you said we have a reasonably good idea how many of these planets are. I mean, really? I mean, it's one thing to say there's on average 1.6 planets around every star in our galaxy based on this patch of sky in Cygnus that Kepler looked at. But I mean, you can really say with all this 90% confidence that you're going to find 1,250 exoplanets in the 2-minute mode. Okay, so we really have that good of a handle on what kinds of planets and how many are out there.
So in order to do that, I mean, the work that Tom's talking about has been done by a lot of, extraordinarily hardworking people affiliated with Kepler, people like Chris Burke and Justin Christensen and Jeff Coughlin and others that basically analyzed the 160,000 stars that Kepler observed over 4 years and very, very precisely figured out how many kinds of planets of which type and which orbit it actually found, and then extrapolated from that, or really much more sophisticated analysis, figured out what is the underlying population frequency of these different types of planets. And that's what we took as the basis. Then we could take that and basically populate these modeled planets around the known stars that TESS is going to observe, and that's what gives us our yield of planets.
Okay, all right. So it's important to note, though, that the kind of information that TESS is going to get will just give you a count because it's only looking at transits. What other information, besides knowing that there's a planet there that passes in front of the star, causing it to be a little bit dimmer, what other information can you gain from the transit method that TESS employs about a given star system?
So the primary information from a transit are really just how long it takes to go around its star and how the size of the planet relative to the size of the star. So if you know how big the star is, you can measure how big the planet is. But for almost all transits, that's where information stops. That's all you're going to get. And really, TESS is the finder scope for other ground-based and space-based telescopes to come. Some of these are going to be measuring the mass of the planets. So with the radius from and the size of the planet from TESS and the mass from ground-based radio velocity telescopes, you measure a density. And with a density, you can start to understand composition. So is this planet very light? Is it a gas-dominated planet? Or is it rocky, like our own world? And then you can start to understand, well, if something's maybe twice as big as Earth, is it likely to be rocky? Or is it likely to be gassy? What about 50% bigger than Earth? These are questions that we started to scratch the surface off with Kepler, but TESS is really going to solve that.
That's a great point. So with the transit, you can say that that planet is going around its star. You can get its year, you can get its size because you can tell how big the dip is. That tells you how big it is. But you need more information. And the radial velocity method, which we've talked about many times on the Hangouts before, that it measures a wobble of the spectrum of a star. That can give you its density. And from that, for the size versus the density, you can start to talk a little bit more about the planet itself. Is this interesting? That's why everybody, I think, got so not bent out of shape, but went nuts about TRAPPIST-1, right? I mean, that was all these planets. They had years that were really great around this dwarf star, and they were Goldilocks-y and all that stuff. But they were able to gather that these are rocky planets. And you can't, TESS by itself can't tell you that, can it? It can only tell you, there's a planet here, here's how long it takes to go around the star, and here's how big it is. Right?
I mean, that's really it. However, what TESS will tell you once you have that data is going to tell us about the size of planets. We're going to collect a whole bunch of ground-based data, which is going to tell us the mass of planets. We're going to start to understand how composition scales with, say, size. But once we have that information, say we find another planet that's Earth-sized, TESS will have told us already, well, that's going to definitely be rocky, or perhaps that has a 70% chance of being rocky, because we'll have learned how size scales with composition.
Yeah, and I would comment that at least my understanding of the design of the mission is that the fact that it's looking at the whole sky, that's a great statistical sample, but it's also brighter stars. And as was mentioned, some of these objects can be observed from the ground. And so detailed studies, once they're found, it's hard to find them from the ground, but once you have this survey, then you can do some observations from the ground and some from space. So you can get more than just orbits, right? You can, and possible sizes, you're going to get all kinds of characteristics. Then we can really talk about what are exoplanets.
That's right. I mean, really what TESS, the value that TESS has is, I mean, it'll certainly tell us a lot of information about the planets themselves, but as Tom mentioned, the real goal of this is as a discovery tool. This will actually tell us where these super exciting planets are orbiting bright stars that are near the Earth. And then what that'll tell us is where to go with these big, huge telescopes that are being built in Hawaii and South America, or the space telescopes like Hubble and the upcoming Webb telescope. And those will be usable to actually find all this other information that we don't actually learn just from TESS. So TESS is the finder, as Tom said, TESS is the finder scope. Then we actually get all the really good information about atmospheres and orbits and composition from other surveys.
Okay, hang on. Someone just crashed our Hangout now. What who is that down? I think that is another author on the paper. Is that Elisa? Is that who that is? Oh, she went away.
She switched off. I think she clicked the link.
She joined our link. Okay, but I don't know why she's not. She was unable to make it. I think is what she told us. But there she did. She showed up. There she was. She was the third author on that paper, folks. Okay, so that's what she looked like.
We should probably talk about.
Yes, I'm glad you did that, Carol. So let me remind you, you are watching the Astro Coffee Hangouts that are sponsored by the American Astronomical Society. And Carol, why don't you talk a little about what they mean?
The American Astronomical Society, as some of you know, is our professional society for astronomers as well as other people interested in astronomy. And we have annual meetings and also a lot of topical meetings sponsored or co-sponsored by the American Astronomical Society. And we have a lot of education and outreach programs that come out of the members and are coordinated through the American Astronomical Society. So we're really glad that they're sponsoring the Hangouts, because this is the way of sharing and showcasing the kind of research that's going on now by the members. And so we get to talk about all kinds of things, from distant galaxies to the latest launches and the research. So you get to talk to the researchers themselves, rather than me telling you what I thought the paper said. So, which is more typical of astronomy coffee in a department. Usually we sit around and talk about the research that we've read. Sometimes we have an author come in who's going to give a colloquium and we talk to them. But this way you can share with the researchers what they were thinking, why they did the study, and what they discovered, and what they're going to do in the future.
Good,
so
thank you.
Thank you, AAS.
Thank you so much. Yes, this is a great outreach effort by these guys, and I'm very grateful for it. So we are talking about the Transiting Exoplanet Survey Satellite, which was launched a couple of weeks ago and is now on its way to its science orbit after it encounters the moon. And I believe we said May 28th is when we're going to be there. Is that right, guys?
That's when our lunar flyby is, yes.
That's the lunar flyby, and that puts us in the proper orbit for TESS to start doing its scans, which it will do over the course of 2 years. And lots of questions, so let me get to a couple of them. Peter Q was commenting, the Kepler was awesome. This is on Discord. The average population of the universe is still 0. Okay, I don't know how you get that, Peter. But anyway, he goes, as I was saying earlier, I hope we find something wonderfully weird and unexpected. Are you guys hoping for that too with TESS? Are you guys sound like with this paper, you pretty much know what you're going to get, right?
Yeah.
You don't want weird and unexpected. You want what your paper says,
No,
right?
We want both.
Okay.
Yeah.
We want to find all of these planets, all of these thousands of planets we talked about in this paper, but we're also really, really excited about all of the extra stuff we're going to find. One of the things that we didn't even talk about in this paper is the fact that TESS is going to make enormous discoveries that have nothing to do with planets. Things like binary stars and pulsating stars and systems doing all kinds of weird behaviors, because it's going to look at the entire sky with the precision that Kepler had. And so that's going to be super exciting for studies of stellar astrophysics and the environments of young stars and star-forming regions. So there's a lot of really cool stuff we're expecting.
I think they call that transient astronomy now. I mean, this was a thing that was completely unheard of, say, 50 years ago, where everybody thought the universe was a very static place, nothing ever happened. But now they've got this transient astronomy idea where things change. You know, supernovae clouds expand, and
we come to call it time domain astronomy.
Time domain astronomy. That's a better.
All these surveys that take place over time for people who are really excited about. In 5 years or so, the Large Synoptic Survey Telescope is going to be going online, and that's going to do huge things with time domain astronomy.
It's going to look at the entire sky like every couple of days. So I mean, it's going to have so much data. That one's I'm very excited about that one too. Okay, couple questions. I'm going to start with Atom Synergy's one that I don't understand, but I will ask it anyway. Will TESS data help nail down the distribution of planets around the Fulton Gap? I don't know what the Fulton Gap is.
Oh, I do. I probably.
Tell us what the Fulton Gap is.
Yeah, absolutely. So this idea of the Fulton Gap is B.J. Fulton is an astronomer, and he found that planets seem to either be smaller than, I think it's about 1.6 Earth radius, so 60% bigger than the Earth, or they seem to be larger, but there's a gap around about 60% bigger than the Earth.
I didn't know there was a name for it. Okay.
Yeah, and the thought of these is that if you're in that kind of gap, you either you boil off your atmosphere, so and you become kind of a barren planet with no kind of thick atmosphere, which means you're smaller, or you're bigger than that and you keep all your atmosphere, and you're a super Earth, but you're not anywhere in between. But this is a fairly new study from last year and the year before, and we'll certainly learn a lot more about planets and planet sizes, especially in that kind of size range.
Good question, Adam. God, you always go with good questions there.
Is that right, Josh?
Yeah, no, I think so. I think certainly. I mean, TESS is going to find a lot more planets. Will populate more of the Fulton Gap of space. Basically, those small planets and the slightly larger to get more objects in that area. But I think it'll be augment what Kepler has found. Achilles
308 is asking. Oh, I'm sorry. Go ahead and finish.
I was going to say just the real kind of sweet spot for both TESS and the Webb Space Telescope is these things we call super Earths, which are somewhere between 40% and bigger than the Earth and about twice the size of the Earth. They're really interesting because we don't have anything in our own solar system that looks like that. And TESS and Webb are going to be great observatories to study these and understand what they are and their processes. They're really cool because they're probably the most common planets in our galaxy. Certainly the ones we find the most frequently.
Super Earths.
We really don't have a good handle on them.
Yeah, I was an article that came out. There was a paper coming out also on Astro PH that outlined what it would be like to try to launch a rocket from a super Earth. It's not easy to have a space program if you live on super Earths, because it's bad enough from Earth, but can you imagine 2 and 10 times the size of the Earth would be quite difficult. Okay, well, you brought up JWST, so I want to ask you about this. The idea was initially that TESS would be up there for 2 years doing its thing, and that the JWST would be launched in October 2018, and there would be a nice complement of both telescopes at the same time. TESS would go, oh, hey, JWST, look at this is cool, and JWST would go, thank you, okay, cool, yeah, that is neat, and here's what I found. But that's not going to happen now, because JWST has been delayed until May of 2020 at least. How does that affect? Does that affect anything with this dynamic? I mean, is it just going to be delayed, or does it really change the mission for TESS in any way at all? This delay of JWST.
I don't think it really affects TESS. If anything, it's almost a little bit good. I mean, the delay is always, of course, an inconvenience and a difficulty for a lot of people. But as far as TESS goes, when we start finding planets with TESS, they'll still be there when JWST launches. So from the very narrow perspective of using JWST to observe the atmospheres of TESS planets, if JWST was delayed 1 or 2 or 20 or 150 years, there's no reason why I couldn't still observe those planet atmospheres.
An interesting planet, an interesting planet found by TESS is still going to be interesting a year later or 2 years later. Right?
Exactly.
Yeah, like Josh said, we're of course always disappointed when things don't happen right away. But now TESS will have completed its 2-year survey and found all those great planets, and we'll be able to observe them right away when James Webb is flying. The planet we find in the last month of the TESS primary mission can now be one of the first targets observed by James Webb.
You know whose life it makes difficult, Carol, and I bring this up because you know about the time allocation committee. After TESS launches, everybody's going to have all these.
Thinking of that, there's going to be a big fight. What's the most important thing that we can possibly do with James Webb? Right?
That's right.
It's going to be a mess.
Big fight.
That's right.
Whereas when there are only like a handful of planets, then it would have been easier, not easy, but easier. Now it's going to be a mess. That's what they pay them the big bucks.
That's right.
And also, those of us who do exoplanets find it almost inconceivable that people actually want to use JWST to do things like observe galaxies and cosmology and quasars.
Who cares about the first galaxies in the universe?
Use it all for the planets.
I know.
I've because I work on the Hubble mission, I have, walked that fine line, and I said, I'm telling you guys, JWST is going to make its name in exoplanets.
You think so?
Universe stuff is cool, but yeah, I do.
Oh, wow.
I think it's going to be all about exoplanets.
Oh.
That's not to say there aren't going to be amazing discoveries of distant universe, because there will be. But I mean, look at now Hubble even, right? I mean, we're always doing stuff on exoplanets now when that was never the intent. So, yeah.
And one thing to also say about this is that it's, we're all now expecting Webb to do amazing things for exoplanets.
Yes, I know.
It's worth bearing in mind that Webb was not designed to do that.
Right.
Webb was originally designed back in the 1990s before more than a handful of exoplanets have been discovered. None of them had ever been seen to transit at that time.
Right.
And but it was designed to be so flexible and so versatile of a telescope that now it's going to be, we expect it to be a fantastic tool for studying planets.
Nobody thought that there would be a transit observed by Hubble.
And I think that's really a testament.
That was amazing. And even some hints at exoplanet atmospheres.
And I think this is just,
you never know.
It's a fantastic testament to the ability of NASA and the mission designers who worked on Webb to do such powerful,
clever people like you who figure out how. I mean, I'm always amazed at the observing techniques that people come up with and how they reduce their data. It's like, you want to do what? Oh, very interesting. So yeah, I think it's a combination of engineering and also ingenuity on the part of the researchers.
Well, to me, the Saving the Mission Award still goes to the Kepler guys who turned Kepler into K2. That still blows me away. The way they figured, hey, wait a minute, it's not dead yet. All right. So let's.
Actually, I think WISE had a good record. So.
Oh, that's right. WISE was actually turned off. And then turned back. It was something else before, and then they turned it back on and go, "Hey, let's do near Earth objects."
Hey, let's
do
this. Like what?
That's right.
Sure.
That's a good example.
Right. Yeah,
that's a good example. You get your money's worth with NASA, folks. You just do.
I think so
you just do. Now, the exciting thing about JWST will be that it can have it has near spec on board, which will give us a hint about if a planet does have an atmosphere. We'll get some information, hopefully, about that atmosphere, and that'll be very huge.
Now, just say near spec. You have to explain what near spec
near
is.
infrared spectrometer.
Near infrared spectrometer.
Right. That's right. And as we all know by now, hopefully, that we know that the James Webb Space Telescope is an infrared telescope because the future of astronomy is in the infrared. I knew that'd get you, Carol. Okay, I was told that by my professor, but I was told that back, like 20 years ago. Okay, Achilles 308. Won't the brighter stars TESS is looking at pose challenges for life living on the planets it finds? The brighter stars that TESS is looking at, will it pose challenges for life living on the planets it finds?
Well, actually, with TESS, most of the reason the planets are brighter most of the reason the stars are brighter isn't because they're intrinsically brighter stars, it's that they're much closer to us. if a car is far away, its headlights aren't very bright, but they're still the same intrinsic brightness, but they get very bright when they get close to you. That's what we're doing with these stars. Typically, stars observed by TESS will be 10 times closer than those observed by Kepler.
It's the little red ones, the little M dwarfs that are nasty with their flares and stuff,
they are
right?
Nasty. Those are nasty little stars. They are
nasty little.
Actually, in terms of one thing that TESS is really going to clean up in and do some fantastic science is studying the frequency of flares on cool stars.
Yeah.
We're going to observe thousands, tens of thousands of M dwarfs, red dwarfs, and we're going to just learn how frequent are they, both the function of kind of temperature of the stars, but also of age of the stars, because we'll observe both young M dwarfs.
Yeah, that's true. Yes, right. Yeah. Exactly.
Can you give us an idea how far, when you say the closest stars to us, that's what the TESS mission always says. How far out are we talking about here? What's the radius of distance that TESS will be looking at away from us?
Yeah. So TESS planets are typically something like 30 to 100 light years away.
So 100 light years.
Yeah, it's somewhere between 30 and 100 light years, whereas Kepler's were more like 300 to 1,000 light years away.
Okay, here's a question from D Physics Star. Actually, there's 3 questions in here, but I'll start with the first one. Can TESS detect circumbinary planets? By the way, guys, thank you for using the question mark. It helps it easier for me to see. Can TESS detect circumbinary planets? I'll start with that one.
That's going to be hard. So,
what's a circumbinary planet first?
Tatooine.
Tatooine.
It's when you have a binary pair of binary stars that are orbiting each other, and then outside that combined binary pair, there's a planet that's orbiting both stars. So if you're standing on that planet and you look into the sky, you see 2 suns.
Right.
So Kepler has found, I want to say 12, 13, 14 circumbinary planets so far, something like that. So we know that they exist. So we know that there are planets orbiting binary stars. The difficulty with finding them is that you have to, in order to find a planet using the transit method, you have to see multiple orbits. You have to see multiple transits. It turns out that Kepler showed us that let's say you've got a binary pair of stars that are orbiting each other once every 3 days. The planet has to orbit significantly further out from them in order to be in a stable orbit. So the binary pair is orbiting quickly. The planet is orbiting over, maybe 5 or 10 times longer than it takes the stars to orbit. And TESS is only observing most stars for about 27 days. So most of those stars will not be observed for long enough to find multiple transits of a planet around a binary star. The places where you might be able to do that, though, will be in those caps on the top and bottom of the hemispheres that we looked at earlier, those continuous viewing zones. There, TESS is observing for 350 days continuously, and that's, if we're going to find circumbinary planets, it'll be there.
Yeah, there's going to be a bias here, isn't there, built into the observing program? You're going to be seeing those planets that have relatively short years, just because of the observing time that you're doing this. You're going to miss the planets that have like multi-year years in them. Okay, good question. Can TESS detect planets around B and O type stars? This is still from Physics D, or D Physics.
Josh, you do hot stars.
Yeah, so B and O type stars are the hotter, bluer, brighter, bigger stars than our sun. The short answer is we probably won't detect many planets around B or O type stars for a couple reasons. One is that because the stars are physically larger, a planet of a given size makes a smaller dip in brightness as it goes in front. It blocks less of the total surface of the star. So we think that TESS will find planets orbiting A-type stars, which are just a little bit cooler and redder than the O and B stars, but it'll still struggle even to find gas giant planets orbiting O and B stars. The other reason that's difficult is O and B stars don't live very long. They only live, maybe a few tens of millions or maybe 100 million years. And we think that most planetary systems take, they don't take that long to form, but it takes time to form planetary systems. And finally, O and B stars are physically so large, at least the O stars, that I'm not sure if a planet could be close enough to be in a stable orbit around an O star, not be inside the O star, and still be detectable by TESS. I'm not sure what the numbers are.
Okay. Well, then, of course, the follow-up question on that was, what about brown dwarfs? Can you detect planets around brown dwarfs? Which I'm going to...
That's going to be really tough.
I know
the problem is TESS is mainly built to observe planets orbiting relatively bright stars, and even the very closest brown dwarf to the Earth is so intrinsically dim that even the very closest ones look exceptionally dim. So I don't know if any brown dwarfs will be bright enough for TESS to be detecting planets around them. That's a good question. Thomas, do you remember what the smallest star is that were in our simulations?
So TESS is sensitive to slightly redder light than Kepler. It goes actually redder than our eyes, slightly into the kind of the infrared, which is where brown dwarfs are brightest. However, brown dwarfs are still extremely faint. They're just so small and so cool. We may find one or two. We might find some binary brown dwarfs, those kinds of things. We're looking at a lot of sky, so it gives us a lot of opportunities to find rare events. But I wouldn't expect to find large numbers of them.
Boy, you guys are like really into different kinds of spectral types in your stars and your questions. Condor Boss, how many F and G type stars are on the list? These guys know their stuff, right? I mean, I'm not kidding around. These guys know. The people who watch these Hangouts, they've been around. What about F and G type stars?
You know, actually, F and G type stars are really TESS where we'll probably find most of our planets. TESS is really focused on finding small planets, which are mostly going to come around the smaller stars. But F and G stars are very bright. You know, a lot of the stars we see in our night sky are F and G type stars. Therefore, we can see them quite far away. So we're going to find a lot of sort of Neptune size and a bit bigger than Neptune size planets around F and G stars. Absolutely.
Oh, be a fine girl, kiss me. That's what I remember.
Stop.
Okay.
Ew.
That's very incorrect. Politically incorrect these days, isn't it?
Yep.
Let's see. D-Physics star. After the 2 years, this is a good question. After the 2 years nominal mission, what's the plans for an extended mission? You're not just going to turn it off after 2 years. Come on. We're done. Turn it off.
I expect we won't decide we're done. So we have a 2-year mission because that's what we need to do this experiment. It's a 2-year science experiment, but the hardware we build is fantastic and can do so much science. So we're going to propose to do different and new science with the spacecraft. What that'll be, I think we're working through some of the ideas. One would be to perhaps do a deeper survey of a smaller fraction of the sky, maybe filling in the gaps between where Kepler and K2 are sensitive and where TESS is sensitive. But there are many different ideas of what we might do. Kepler right now, the Kepler spacecraft is doing a supernova survey. That is certainly something that Kepler was never thinking of doing in the past.
That's right.
So who knows what exciting things we can come up with.
You know what I've discovered, Carol, after all the years we've been doing these Hangouts, is that astronomers are very superstitious. They don't like to talk about extended missions. They don't want to jinx the one they've got, right?
Well, yeah. There's
cautious.
Yeah.
I wouldn't say superstitious.
Yeah, there's politics involved in that too.
Yeah, that's true. But it is. Yeah. I know.
Don't count your ducks and all that.
I know exactly. Well, you don't, right? You don't want to take for granted what you want to get done. The thing you said you're going to do first before you even look past that. But it is a trend with NASA missions that they squeeze every bit of science that can be done with almost everything they've built. So it's reasonable to think you'll get some fun out of this after 2 years too. Achilles 308 this is a weird interesting question, but is TESS sensitive enough to detect microlensing black holes? So that's where a stellar-sized black hole might move in between the distant star and us, causing a very strange lensing signature that you would see in the light curve. Can it see those?
I can touch on that because so actually my as well as doing this kind of science and being a scientist, my day job is to support TESS to do science that isn't related to the primary mission. So to do these kind of interesting studies, be it flare stars or supernova or galaxies, but one of our studies that we're supporting is to find black holes in binary star systems with regular stars. So you're looking for stars that regularly get brighter because they have a black hole in the system that will act as a lens and lens them towards us.
Wow, I didn't even think of that to ask that. That's amazing. That's an amazing question. Good. Okay. Let's see. Alexander Reinders is asking the loaded question: when will JWST definitely start? May 2020. Okay, there's no definitely here.
Definitely.
Remember, those are launched not before dates, and there's at least 6 months of testing JWST before you get guest observer science.
Right. Is there going to be a commissioning period for TESS when it gets into it, or are you commissioning it now as it heads out to its final orbit? Like for example, are you going to be, has first light already occurred, for example? Have you already taken some images with the camera, or are you waiting until you get out there?
So we're commissioning now. The cameras, I believe, were switched on yesterday. However, the cameras are still warm. So we're not taking science images or anything like that yet. We wanted to know, are the cameras functional? And everything I've heard has been super positive. And we're gonna keep taking data as we go out to our final science orbit. Everything's cooling down, everything's getting into its kind of operating temperature. And then once we're in our final science orbit, we're going to do one practice orbit, check everything out, go through both the spacecraft and then our ground system, okay, and then we're into science operations. And that science operations should start towards the end of June.
Okay, all right. So, and then I believe, if I remember what from other Hangouts, what Sarah and others have said is that the data will be available immediately, right?
That's right. Everyone in the world can access the TESS data as soon as it is downloaded, reduced, and posted on the server. So anyone out there, if you want to go look for planets, you can go do it.
Carol, is it going to MAST or is it going somewhere else? Do you know?
It's going to MAST. I worked on that part of the proposal, actually. Helped write that. And also there was an education and outreach program as well. But yeah.
Okay, good. Well, there you go. So MAST is Dean Mikulski.
Its cousin.
Yeah, that's where you get Hubble Data too, folks. It's Mikulski Archive for Space Telescopes, and TESS data will be there. Hubble Data is there, along with Kepler and other missions as well. So you can use it, get it, and process it yourself. We've had many. We have one spaceman. Her name's Judy, and she's really good at processing this data. Does amazing work with raw data herself. So it can be done. Let's see. The TESS orbit, the TESS orbit is genius too. Yeah, that was just so you could, that orbit is just so you could get the sky coverage you wanted, right? Is that why it's in this orbit that we're putting it in? Hello?
Tom, you want to?
Oh, sure, I can touch on that. Really, the orbit is that orbit that gets us the good bandwidth whilst spending most of your time relatively far from Earth in this kind of stable environment. It also allows us to look at the same part of the sky for a long period of time. We look at the same part of the sky for about a month. And so this kind of orbit has been used once before. It's not the exact same orbit. TESS's orbital period is half the Moon's orbital period. So the Moon takes about 28 days, and we take about 14 days to go round. Okay. IBEX was a mission that took a third of the Moon's orbital period to go round. So that's the closest kind of comparison to our orbit.
Okay, all right. And so the let's see. I just scrolled past the question I was going to ask. I know there's this is from capital H. I know there's a lot of overlap between M dwarf planets have short periods, but other than those exceptions, why only 27-day view periods? Why only 27 days?
I think that's a function of our orbit.
Okay.
You're going round, and you only have such an angle relative to the Earth and Sun you want to be looking. We want to keep our solar panels facing the sun, and we want to keep our cameras facing away from the sun. So that only gives us a certain amount of flexibility. Plus 27 days is what we need to do our science. That gets us, say, 3 orbits of things with an orbital period of about 10 days. That gets us plenty of kind of temperate planets around M dwarfs, as well as hotter planets around hotter stars.
I suppose it had to be asked. Peter Q is going, will TESS be hit by a space Tesla in the future? I suppose someone had to ask that
Space
question.
what?
Space Tesla. There's a Tesla up there. I don't think it's going to be anywhere near TESS, though.
Hopefully not.
All right. Well,
I don't think Elon's that dumb.
Yeah. Abdul Qadir Almami is asking, and I suppose since you guys were very specific about your numbers in your paper, we may as well ask this too. How many Earth-like planets in the habitable zone will TESS find?
TESS, this isn't really TESS's sweet spot, but we predicted a couple of planets, 2 to 3 planets about Earth size, maybe in the kind of habitable zone of pretty cool stars. Maybe double that around kind of slightly fainter stars. But TESS isn't optimized for habitable zones, really. It might do a few.
That's because the ratio of the planet sizes and the dimness and the light curves are going to be on the edge of what TESS can optimally see.
It's not so much the depth of the transits or the precision of the light curves. It has to do with the orbital periods that we're sensitive to.
Okay.
If we wanted to find more habitable zone planets, we would have had to go into a completely different orbit, more like Kepler, where you can stare at one patch of the sky for years on end. The problem is, if you do that, like Kepler did, it's a great way to find planets in the habitable zone, but you can only look at one very tiny portion of the sky over that 4-year period. And we wanted to grab everything over the whole sky, and that basically forced us to not be able to dwell on any one part of the sky for a very long time.
Okay. Well, we are out of time. I will stop it there. I want to thank our guests, Dr. Thomas Barclay from the Goddard Space Flight Center in Maryland, and Dr. Joshua Pepper from the Lehigh University, both of whom have written a paper. The link is in the description box on what the exoplanet yield they expect to have from the Transiting Exoplanet Survey Satellite, or TESS, and it's a really interesting paper. They've really covered a lot of stuff and how they know what they know, and we've covered a lot of this here today and answered some of your questions. I, for one, am very excited to see TESS get underway. It is currently on its way to its science orbit. The end of May, we should be hearing a lot more about it. The data will be available on the MAST archive. You can get it yourself and see for yourself what's going on with the TESS mission. So I want to thank you all so much for taking time out to watch. And Carol, thank you for putting this together.
Thank you very much. Yeah.
Yeah. All right. Well,
thanks for having us.
Yeah, it was great. Thank you so much.
Hey, maybe after TESS gets going, and you get some results back, maybe we can do another one. Kind of see how you're doing.
Yeah.
Maybe do a tally. See if you're on the right track. You know what we should do is we should do one of those boards like they do in March Madness. You know, where we place bets to see who's going to get the most accurate.
Yeah.
What is the exact number of exoplanets we're going to find?
Right.
Okay. All right, folks. Well, I want to thank you guys so much. And as always, and thank you guys for watching. Next week, I'll be back with Harley Thronson in Future in Space, where we will be still talking about TESS again, only this time it will be about some of the instrumentation on board, the cameras themselves, the engineering, and some of the astronautical stuff that went into the spacecraft itself. So join us for that. I believe it's next week, and I will put that on the calendar also. Don't forget, please like this Hangout. If you watched it on YouTube, give it a like, share it with your friends, talk about it, help us get the word out about these Hangouts. We need your help. We like your support just by being there for us when we're doing these streams. So thank you guys all so much, and thank you for watching. And as always, keep looking up.